Sorry, guys, I forgot to record, so I enabled that. Next, we'll discuss the coupled oscillators. So we have a key example of coupled oscillator, which is the tuned mass dampener system, right? Where do we see tuned mass dampener system in the real world? Well, we see it if we're trying to limit the swaying of tall buildings in the wind, right? It's like skyscraper, right? The wind comes along, the skyscraper is swaying, and the building shakes, right? And we don't want that. We don't want that to happen. We want safety, right? There's safety regulations. So you need to limit the swaying of tall buildings in the wind. You can also use it to stabilize the laboratory tables, right? Because if they're sensitive to vibrations and the table is vibrating, that could mess up the experiment, right? So we should stabilize laboratory table. So in our analysis, we're gonna heavily rely on spring mass dampener systems, right? And so you guys are familiar with springs from Hooke's law, which we discussed earlier. But there's also the dampers, which basically resists the velocity. It's proportional to the first derivative of the position, right? Which is the velocity. So with some notation, we have x1 dot refers to the first derivative of x with respect to time, or change in the position over change in time. We also have the acceleration. You can use like double dot, right? So this is the x2 double dot, can be written as the second derivative of x with respect to time, or the change in the x over change in time. And then there's like another, it's like a second order, right? But for now, you can think it's the acceleration, right? So here I know that we have a lot going on, but let's break it down into pieces. You have a primary mass, which is like your building, and then you have a secondary mass, which is what you're using to stabilize the building, for example, right? And so this left, you can kind of think it's like the wall of the, you can think it's like a wall or something. It isn't fixed. So you have a primary spring and a primary damper. And you have also you have a forcing term, right? So you have like the wind comes along, and it's a forcing term on the primary mass, and the displacement of that mass is represented by x1. Similarly, you have the secondary spring, secondary damper, and the dampers resist the velocity, remember that? And you have the secondary mass. The x2 will be the displacement of this secondary mass. And so what we can do is we can create a system of equations, right? So for the first mass, let's try to figure out how many terms we should use in our analysis. This primary mass, we know that we'll have a term for the spring, K1 over here you can see. We should also have a term for this damper, which is B1. Similarly, we should have a term for the spring and the damper on the left. So far we have, what, 4 terms? We should have an acceleration term for this primary mass, which makes 5 terms. And then you should have a forcing term, which is like the wind that comes along and sways the building. So that's like 6 terms altogether. And so that's what's precisely being shown in this first equation here. And so this is basically just an F-net equation at the end of the day, right? These both are just F-net equations. And so we write the m1 x1 double dot is our mass times acceleration, right? And then you could take the b1 and b2 terms. These are damping terms, right? One of them is simply on x1, right? It's between like the primary mass and the wall, so it's just b1 x1 dot. And then you have the second damping term, which is, you can see it's between the two masses, right? You can see it's this dampener right here, this dash pot or damper, for example, is between the primary and secondary mass. So it involves the differences between the masses, right? And then similarly, you have the springs, which you're familiar with from the Hooke's law, right? There's supposed to be a K1 here, sorry guys, K1 X1. I accidentally put K here, it's K1 X1. And that's the Hooke's law. And then there's a Hooke's law interaction term between the two masses. So all of this summatively will help create the first equation. It's a big, complicated equation. We do make some simplifications down the line. Next, we have a second equation, which is formed by similar process. It's an F-net equation, and it uses the dampener between the secondary and first mass, and also the spring between the secondary and first mass. Right? There's only 3 terms, the acceleration term, and then the 2 interaction terms, which are the dash pot and the spring. So that's what helps us to create these 2 equations. They're simply F-net equations. Next, we want to convert this to a first order system and also divide out the mass for simplification. So basically what we mean is that this is a second order system that we had back here because it involved the second derivatives, right? x1 double dot, x2 double dot. We want to simplify by using first derivatives. So we use this trick. Let's define 2 variables, y1 and y2, which we'll define to be the derivatives like x1 dot and x2 dot, right? And you can say that y1 dot is also x1 double dot and y2 dot is also x2 double dot, right? So that's why you can see the acceleration term here replaced by y1 dot and then y2 dot over here. So we replace the acceleration terms. We also replace x1 dot with y1 over here. And we basically make the corresponding replacements. The x1 stays the same, but we replace the derivative terms, right, with the y terms instead. And also we divided out the masses as an algebraic simplification. You can see here we divide out like m1 on both sides on the first equation, and the second equation we divide m2 on both sides. So this is using algebra, right? Using algebra, and then also making this cool trick right here to convert into a first order system. And so now this is completely the first order system here. And also one thing to note is that we have 4 variables, right? We have like the x1 variable, the x2 variable, the y1 variable, and the y2 variable. And that's significant to note as we continue to the next step, which is about converting this into a matrix equation. Now I know this is a bit complicated, but bear with me here. You have a matrix equation. And so let's just start with these first two right here. This is 0, 0, 1, 0, and then 0, 0, 0, 1, right? We'll start there, right? So basically, these terms are simply a result of our conditions, right? y1 equals x1 dot, y2 equals x2 dot. You could convert those using the process of matrix multiplication, which you might be familiar with from like pre-calculus, for example, right? And so, you know, this 0 like multiplies with this x1, you can have this 0 with this x2, right? And this 1 corresponds to this y1, right? So this says that x1 dot is this 1 times y1 over here. This x2 dot is this 1 at the far right, this 0, 0, 0, 1, this 1 over here times y2. So these first 2 right here are just these 2 equations. Next, we grouped some terms in our algebra and divided out the masses, right? So this y1 dot, you can see it's just so this part right here, this negative k1 plus k2 term right here, multiplies with the x1 term up here. This k2 over m1 multiplies with this x2 term, and so on and so forth. You can use matrix multiplication to kind of decipher the equation, right? But basically, this equation is just the same as what we had back here. This is just a slightly neater representation. And we can use the matrices to find eigenvalues and then later eigenfrequencies. We can find the normal modes to the system. We can create analyses. And using this, we can solve the problem, basically. We have to use like computing software, like Mathematica or MATLAB or Maple or even like GNU Octave. Mr. Nauman used like Python in his analysis, right? And we'll take a look at his video regarding that. One more thing to note is that on the right, we have this f over m1, right? Which is just this f1 of t divided by m1. It's the same thing over here, it's just inhomogeneous. Many times you will simplify and not consider this, but sometimes you can also consider this as well. Using computing software, it makes a lot of this a bit easier. So now let's play Mr. Nauman's video to get a better idea of these concepts. So I know that there's an option to optimize this for the video screen sharing. Alan was mentioning a bit last time. So let's see if we can make an optimization here. All right, I think I'm ready to play the video. Let's see if this works.
All right, hey, good morning. So this is for the physics club, and I wanted to talk to you a little bit about coupled oscillators. A coupled oscillator is a bunch of springs that have different spring constants. They're all connected to each other. And if you pull in one and let them oscillate, they're going to oscillate each one of them at different frequencies and with different displacements. And so what you do is you set up an equation of motion here, which is a differential equation. It results in an array, a matrix solution, which I'll show. And it turns out there's certain solutions or certain initial conditions of these springs that allow them to oscillate at the same frequency. And there are other cases where they oscillate kind of randomly and not in sync. And so one thing you can look at is, this is a time domain, right? What's happening with each of the springs and their position versus time. But you can also look at frequency using a FFT fast Fourier transform. And you can see what it looks like in frequency, right? And so here you can see there's 3 different frequency peaks. And so what I'm going to do is I'm going to show you the code that I've been running, and then also I'll send you guys a copy of the code. And if you want to run the Python code and tweak it and play with it, that would be wonderful. So let's see if I can find it. So here's the code. And I can hide this panel. So I'm going to run this. I won't explain it all. There's a Runge cut of 4 solution for solving the differential equation that I won't get into. This variable x011, those are the initial conditions of each of the springs. These are the velocities. They're initially at rest, but I stretch them a certain distance. And then I go through a bunch of time steps. And what I see is, let me make sure. I think I've got the wrong one here. This is the one I want. Yeah, I ran more steps. Right, so you can see these things are kind of not really in sync, but a little bit. They're kind of pulling in on each other. And if we keep going and we plot the power spectrum, right, we can see that spring 2 has peaks here in frequency, and 1 and this should be 3 have peaks at the same frequency, but 2 doesn't have a peak here, right? But they're all oscillating at 3 different frequencies. And so then what I do is I look at what is an eigenvalue or a vector, initial vector that allows them to oscillate in sync. This is one of them. There's 3 for this system. And so here you can see that the mass 2 is not oscillating, but 1 and 3 are oscillating to the sides, back and forth. And since they're equal displacements and opposite, the spring 2 isn't getting pulled on at all. Right, so here's another condition, and you can play with these conditions. Here what's happening is that the green and the blue 1 and 3 are oscillating together, and they're both pulling on 2. Right, here's another third set. Again, very similar. They're all oscillating together, actually, in this case. The last thing, if I go back to the, if we sample this data over a short enough time, what we find is we don't have enough data points in order to get a perfect frequency spectrum, and so we get some leakage. We call leakage when we switch from here to the real value here. These big jumps cause the real frequency in the center to be spread out and have 2 side peaks. So what they do, and what you do, is apply a Hanning window, which is basically to reduce the value or the importance at the edges, right? So we apply a sine function to this, and so we're just looking at this center part. And so that's what's being done here. It's a little bit more complicated, but this is the Hanning window here that I'm applying. And what you can see is that, I didn't show the previous, but you can see that doing so shows that a very clean peak, right? So this isn't that it isn't oscillating altogether. It's really just a matter of the discrete sampling causing a trouble. And so this Hanning window is just a way of cleaning that up and looking at the data and weighting it properly. All right, so hopefully that's interesting. I will send you the code. There's a lot of places to run Python code. I use Jupyter Notebook, but Google Colab is another fun way to do it. And so hopefully you enjoy this and have a wonderful day.
All right, so that was a fascinating analysis by Mr. Nauman right there. We will send you some resources and to try to help you understand some of these ideas. And so regarding like Laplace and Fourier transform is very interesting, right? How you're converting from time domain to the frequency domain, right? So there's a lot of fascinating ideas in here. And then a lot of the analysis that he did, he used like multiple spring mass damping, right? He used like not just like one mass, two mass, but he used like multiple springs in series, for example. Was one thing that they looked at, right? And one thing you notice is that it always goes back down to these FNet equations and the kinds of analyses that we can apply onto FNet equations. So we'll be sending you Mr. Nauman's code, as well as some resources in Python, maybe, and a few other softwares to really help you think about and understand how to do these kinds of analyses. Thank you, everyone.
Thank you. Bye-bye.
Thank you.
Thank you, Rohan.
Thank you, Alan.
Thank you, Rohan. Thank you.
Thank you, Alex.
Bye.
Bye.